Good. Yeah.
Yeah. Can you hear me?
Yeah, sound is working. Yes.
Yeah. Yeah. Let's start. Hello, I am Donggun Kim, and I will be giving student lecture on ship hydrostatics today. Today I am going to introduce the contents of hydrostatic stability in detail. I will teach the definition of a metacenter and how to obtain metacentric height for stability. So first part is definition of metacenter. The typical vessel center of gravity G is higher than its center of buoyancy B. In a floating body, an imposed angle of heel causes the center of buoyancy to move sideways. So to better understand the metacenter, we can compare it to a rocking chair in real life. So the center of weight is higher than the center of support, which on the floor. And when the chair leans back like right figure, the center of support moves and so keep the chair from tipping over. So back to the bezel. When a stable bezel is heeled, the buoyant line of force will intersect the ship's center line somewhere above the center of gravity. So this intersection point is called the metacenter M. So after understanding metacenter, let's learn about the metacentric height, the distance between the center of gravity G and the metacenter M is called the metacentric height Gm. Positive stability is found whenever the position of the metacenter is above the vertical center of gravity. So that is if Gm is positive, it is stable, and if Gm is negative, it can be said to be unstable. So in general, Gm remains essentially constant to for small heel angles. So Gz equal Gm cross sine theta is called the writing arms. So here is a YouTube video that explains GM and the stability.
사운드 옵션을 안 켰는데 화면 공유하실 때 사운드 옵션을 눌렀어야 돼요. 화면 공유 해제하시고요. 다시 들어오면서 옵션 넣으세요.
네.
Metacenter. To understand this, let us recall that a solid body floats in a fluid. If the mass density of a body is less than that of fluid, as in case of wood, plastic, ice cube, etc., and if the weight of fluid displaced by the immersed body is equal to the weight of the body, as in case of boat, ship, etc., when a body, say a ship, floats in water, it is acted upon by two forces. A vertical downward force of gravity, which is equivalent to the weight of the body, W, acting at the center of gravity, G. and an upward vertical buoyancy force, FB, which is equal to the weight of the water displaced by the immersed body, which passes through the centroid of the displaced volume of water, that is, the center of buoyancy. Now, for a floating body to be in equilibrium, the buoyancy force should be equal to the weight of the body. Also, the center of gravity and the center of buoyancy should lie on the same vertical line, called the center line, BG. Now, if a body undergoes an angular displacement, say in the rightward direction, then we see that the volume displaced is larger in the right side. Thus, the center of buoyancy shifts towards the right from B to B dash, and a couple is formed which tries to rotate the body. Here, the point of intersection of the vertical line through the new center of buoyancy B dash and the center line BG is termed as the metacenter of the body, and the distance by which the metacenter lies above the center of gravity of a floating body is known as the metacentric height, GM, which is given by. Depending upon the location of the metacenter, a floating body possesses three types of equilibrium. They are stable, unstable, and neutral equilibrium. When M is above G,
so how do we calculate the GM? If the interpret geometrical in the left figure, GM can be obtained as KB plus BM minus KG. So each term can be calculated as this here. So also we can find the GM of existing bezel as inclining experiment. So this is to explain the process of calculate GM as an inclined experiment. But yeah, but
Today
it's better to skip this video. If you are interested, you are refer to the video. So next is free surface effect. If the ship adhere to one side, the internal liquid will flow in the same direction. This has the effect of reducing the metacentric height. And this effect leads to change of CG. There will be no free surface effect if the tank is completely filled with the internal liquid. So, and we will look into stability in the range of the angle of heel. If the ship is tilted, usually the righting moment will start to increase. Like left side, it increase approximately linearly at small angles, and it will reach maximum at the about the angle of a hill at which the deck edge start to immerse, like the middle section. So beyond that, it will tend to decrease and eventually drop to zero. So at any greater angle to the bezel will capsize. This is about the longitudinal static stability. A ship nearly capsize in the force and the aft direction. So, however, the trim change by adding of or removing or shifting weight on the ship in the longitudinal direction is an important concern. So when hull damage occur, longitudinal static stability decrease and the flooding occurs. If a compartment is flooded, the buoyancy provided by that compartment will be lost. Then the ship will sink deeper and its longitudinal center of buoyancy will usually move and cause stream. Once that goes into the water, transverse stability decreases rapidly. So to prevent flooding, subdivision is applied. Bulkhead are transverse diaphragms or walls to increase the structural rigid and create the watertight compartment. So, next is stability of submarines. So submarines should consider two types of stability. So submerged stability when submerged and surface submerged stability is considered when the submerged, and surface stability is when on the surface. So first, in the case of surface stability, it is the same as the ship we learned earlier. And on the other hand, the stability of a fully submerged body is obtained as follows. So consider GM equal KB plus BM minus KG. The formula for calculating metacentric height learned early. At this time, since there is no waterplane area, so in the submerged body, so BM is equal to 0, so it is erased to 0. So KB minus KG is minus BG, so it is which is the same as GB. So therefore, P must be above G for stability. And last.
We were looking at the differences between.
Yeah, this video is a YouTube video about the difference between ship and submarine stability.
Ships and submarines. Firstly, most obviously, there are huge implications in terms of buoyancy and stability. With a ship, you just need to make sure the underwater part of your vessel displaces enough water to provide buoyancy to keep it afloat. Submarines, of course, are a little different. On the surface, just like a ship, the hull needs to displace enough water to provide positive buoyancy, but it also needs to be able to sink, so you need to be able to increase its displacement to make it weigh more than the water it displaces. It's actually quite simple. You just flood some ballast tanks, making the vessel heavier and less buoyant, basically so that it sinks. That's great for going down, but then when you're deep enough, you need to be neutrally buoyant instead. You want the submarine to weigh the same as the water it displaces, so that it neither floats nor sinks. Again, it's quite simple. You just pump out a little ballast water using compressed air from cylinders. Done precisely enough, you can make the submarine weigh the exact same as the water it displaces, making it neutrally buoyant. So that deals with the buoyancy, but what about stability? After all, a submarine still needs to remain upright when underwater. Remember how a ship uses form stability to stay upright? This just means that the shape or form of the hull provides a right centre. This is how the submarine remains constant no matter how far it leans over. Its centre of buoyancy doesn't move. Instead, you have to rely on keeping the centre of gravity below the centre of buoyancy. Your stability is provided by the force of gravity and the force of buoyancy pulling in opposite directions. Underwater, it's easy because you just make sure the heavy things are placed low down, but on the surface it can be a little harder.
So Yep, that's all. So thank you for listening to my lecture. Thank you.